Yeah, I'm Kathy Whitlock. I'm at Montana State University, and you'll see that both Steve and I list ourselves as emerita, which means that we're retired, but we're still working. Um, However that works. Steve, do you want to say something?
Yeah, Steve Hostetler with the USGS. I actually am associated with the office there in Bozeman most recently for the past 5 or 6 years. And then, yeah, I retired a couple years ago and still working on things that interest me. And this is one of my interests. So this will be fun. Thanks for having us.
Well, we're really looking forward to hearing your presentation and how it can help us plan both short-term and long-term.
Thanks. I thought what we thought we'd do is provide you some context for understanding climate change as it's occurring now. And then we talk about the projections for climate change in the future and what some of the implications are and things that we need to be thinking about. So I imagine this isn't a big group, so we can certainly, we'll try to keep this pretty informal. If you haven't seen it, I highly recommend that you go to the website and look at the Greater Yellowstone Climate Assessment. Steve and I were the lead authors on that, and it's really the first look at how climate change is going to affect an ecosystem rather than a political jurisdiction. And what a great ecosystem, huh? And this assessment also is unique because we look at the watersheds, the major watersheds of the Greater Yellowstone area, and do a deeper dive into what is happening with climate and also with water. And these assessments, this is my third assessment for the region, and they take a couple of years to do because you have to bring a big team of scientists and experts together to put it to write it. You can't just write it by yourself. And then it has to go out for review and meet all the standards of our organizations for quality. But this one, the Greater Yellowstone one, involved universities from the 3 states. It involved federal agencies, most notably Steve at the USGS. It involved nonprofits, state agencies, and we also included the tribes in the assessment. So if you haven't seen it, I think that's really a great starting point for information. Let me just give you the big context on climate change and what's happening now. The best information we have on long-term climate change comes from these ice core records that are taken in Antarctica. And as you probably know, those ice cores sort of layer by layer trap air bubbles that tell us about the composition of the atmosphere going back through time. And so the best information we have on the composition of greenhouse gases and how it's changed over hundreds of thousands of years. The ice cores in Antarctica go back 800,000 years now, the published records. And the blue line is the CO2 records. Here's present day, going back 800,000 years. Blue line is CO2, and the red line is the temperature as it's measured in Antarctica. And you can see that whenever CO2 is higher in the atmosphere, temperature has gone up. When it's lower, temperature goes down, and it's gone up and down within sort of a range of variability for the last 800,000 years. So the times when the temperature goes up and the CO2 goes up, we call those interglacial periods because there's not a lot of ice globally. And then when it goes down, those are glacial periods. And we've had 1, 2, 3, 4, 5, 6, 7, 8 previous interglacial periods, and we're now in an interglacial period. But this one you can see is quite different because the levels of CO2 are off the charts of anything that we've seen for the last 800,000 years. Before we've been in this sort of range of variability, but now we have 420 parts per million of CO2 in the atmosphere. So that's a huge departure from anything we've seen in the past. As a geologist, I always ask myself, well, when's the last time we had 420 parts per million CO2? It turns out that you have to go back 3.3 million years to find the levels of CO2 in the atmosphere that we have today. That's the Pliocene. And this is what Montana, Gallatin Valley probably looked like in the Pliocene. It was 10 to 15 degrees warmer. Global sea level was higher by about 10 to 15 feet. There were no ice caps in West Antarctica and in Greenland. So a very warm, humid world. The reason we don't look like this is these changes are happening so fast that the planet is really in disequilibrium with the levels of greenhouse gases that we have right now. Now, when you think about the Greater Yellowstone ecosystem, our region has been shaped by climate change, right? 20,000 years ago, we looked like the panel on the left. We were covered by a huge ice cap over Yellowstone. The Bridgers had small ice sheet, not ice sheet, but ice cap. Glaciers flowed down all the major valleys. There was about 3,000 feet of ice over Yellowstone Lake. And in interglacial periods, we get these amazing glacier sculpted mountain ranges, these broad valleys with large alluvial deposits. Our landscapes are shaped by past climate change in this region. The funny thing is, or the interesting thing, I guess, is that it only doesn't take much to toggle between these two pictures. With 9 to 10 degrees Fahrenheit cooling, we would look like the picture on the left. In other words, the climate system is really sensitive to temperature changes, and these glacial, interglacial cycles we've had have not been triggered by huge amounts of temperature change. One thing you might not be aware of is that it's been so dry in the past at times that the geyser basins seem to have not been operating. We know, for example, that Old Faithful stopped erupting during a mega drought in 1233 to 1362. In other words, there wasn't enough water getting into the plumbing of the geyser basins to get under pressure to have a geyser eruption. And in fact, trees actually grew on the cone of Old Faithful during this period. People ask me a lot about the Dust Bowl years in Montana, which we know are quite hot and dry. Here's the temperature and drought data going from 2020 back to 1900. So the average temperature you can see in the blue line here, and I've shown the Dust Bowl in this box. And you can see that we're already a lot warmer than the Dust Bowl years going into the 21st century. And so we've exceeded the temperatures of the Dust Bowl years on average. There was a couple of warm years, but on average, we're way warmer. It's interesting, though, when you look at the drought during the Dust Bowl years, the Dust Bowl years were a sustained drought, year-round drought, and happened for several years in a row. And that shows up in this drought severity index as a drop. We are not in the Dust Bowl in terms of annual drought severity, because that's not really what's happening right now with climate change. Here are the trends since 1950. And in the assessment, we start with 1950 because that's when a lot of decision makers were born, you know, and so we're trying to let people try to understand what's happened during their lifetime. For one thing, it's gotten warmer in Greater Yellowstone, about 2.3 degrees Fahrenheit in the upper Missouri watershed. Mean annual snowfall has dropped a lot, and this is taken from weather stations that are mainly below 8,000 feet. So it's sort of a reflection of how much snowfall we've lost below 8,000 feet. And it's really quite astonishing. We've lost 24 inches on average through the whole ecosystem. And what we're seeing just in general, if you look at what's happening with temperature over the 48 states, and then what's happening in Gallatin County, you can see that the graphs show this, you know, this steady warming, whether you're looking at the entire country, lower 48, or you're looking at Gallatin County. We've seen warming, and Gallatin County's actually warmed more than the rest of the 48 states. We've been warming at a rate of about 0.2 degrees Fahrenheit per decade. the US is a little bit less than that. And the reason is because we're a northern state, and the higher latitudes are warming faster. We're high elevation, that makes us warm faster, and we're far from the ocean. So states that are closer to the ocean have had a bit of a moderating effect. Okay, moving more towards the present day, it's no surprise to any of you that we are getting very low snowpack this year. I just printed this off for Montana, and you can see that our region is about half of what's normal precipitation. And some of the areas in the Rocky Mountain front and Helena and so on are even lower than that. But generally, this has been a very low snowpack, an anomalously low snowpack, I should say, as well. And that's looking from 1991 to 2020, which is the period of record. Here's the nearest station to Bridger Bowl, just looking at its record for the year, starting in October 1st. The blue line, the yellow line is the median. So you can think of that as sort of the average over the months. The blue line is the maximum reading, and the red line is the minimum reading based on this 1991 to 2020 period of record. Right now, we're the black line, and we're about 40% of the median, the average. And you can see that we're doing a pretty good job of just tracking the average minimum values. So I'm going to hand it over to Steve because he's going to talk about what lies ahead.
Okay, thanks. Next slide, please. So as you probably all know, we're in a La Nina phase of the ENSO system right now. And what that generally brings on average is kind of what we're seeing in the region, warmer than normal temperatures and drier, excuse me, drier than normal conditions or less precip. So that's pretty much what we're seeing. Also, you'll notice that in the southern US, it generally is colder and somewhat wetter during an El Nino. Next slide. But what we're really seeing here now, this is the average temperature departure from the long-term average for the period November through January. And as you can see, most of this map is yellow and orange. And so what we're seeing here is we're seeing an El Nino effect in the north, but the south is also warm. And what's going on here is this El Nino is kind of overlaid on top of the global warming that's going on. So even though El Ninos are generally expressed as I showed you, in fact, there's something else going on here in the background that's causing warming and therefore no cooling in the south. Next slide, please. So this is the most recent NOAA Outlook issued in December for the January through March season. And as you can see, this has held up pretty well since they started doing this long-range forecast in November. The region is actually leaning towards being above normal through January and March, and normal to below normal precip. So it looks, for right now anyway, the outlook is that what we've seen in the past winter so far is pretty much going to be that way through the spring. Of course, this could vary. These are all probabilities. It could be that next week the storm comes, things change completely. But based on observations and modeling, this is what the near future looks like. Next slide. So to start to look into the far future, the way this is done is with climate assessments. And the IPCC has started doing climate assessments back in 1990. And about every 6 to 7 years, another one comes out. And back in 1990, basically what the assessments looked at was the effect of rising greenhouse gases. As time's gone on, they've gotten far more complex. The most recent one, the emission scenarios, so the greenhouse gas emissions in the future are projected using pretty complex models of population, economics, geopolitical issues, resources, and technology. So it's a very complex process that's done to use all those components to basically project what they think greenhouse gas emissions will look like in the future. But this is all done under the IPCC, who's in charge of these assessments. There's a modeling component called CMIP, which is the Coupled Model Intercomparison Project. So the way we look into the future, we have all this past history, as Kathy's shown you, but the only way we can look into the future is with models. And so that's what the CMIP program does. Next, please. So just a schematic of how this all works. The upper left diagram, a plot, shows you the different possible trajectories for CO or greenhouse gas emissions through the year 2100. And for this particular one, there were 4 different scenarios considered. We're only going to look at 2 today. We're going to look at the top one, the purple one, SSP 585 and SSP 245, because those are pretty similar to the last assessment. And basically what's going on here is that all the scenarios start out in 2016, greenhouse gases increase, but various levels of mitigation determine the ultimate trajectory. So the lower one, the green one, 1.26, is one that has quite a bit of mitigation early on and reduces the ultimate greenhouse gas emissions by 2100. So all of these have some component of mitigation, except for the top one, which is basically there is no mitigation, and it's pretty much continuing as we have been. So what we do with these is we take these greenhouse gas emissions and they put them into climate models. And the climate models have also over time become very complex. They include all the processes shown here. They're very complex, huge computer models, millions of lines of computer code. They run for a long, long time on supercomputers. And what we end up with is a number of simulations from different modeling centers throughout the world of the potential projection of climate for the next through the 21st century. This particular one had 85 simulations. And then in the lower right, you can see that's an example of temperature that comes out of the global climate models. So this is some period in the future, just the temperature over the region at the resolution or grid spacing of the climate model. The next step in this process, next slide, please, is to downscale that climate using some kind of downscaling technique. The particular one in this assessment is a statistical method. And so what that does is take that kind of smoothed out climate data and ends up projecting it over a domain, a 6-kilometer domain that looks a lot like reality in terms of topography. So you can see the greater Yellowstone, the mountain ranges, the Snake River Plateau, and so forth in this map. Finally, this climate data we've run through a water balance model. And so we use the temperature and precipitation and solar radiation from the climate model to generate components of the water balance. And those include snowpack and runoff and soil water storage. So that's how we get from that starting point of greenhouse gas projections to actually having something on the ground that we can look at in terms of the physical system. Next, please. So the data I'm going to talk about here, and the data, also all the data in the assessment, comes from our National Climate Change Viewer. A colleague and mine, we put this together back in 2014. It's a USGS, the Department of Interior site. It has all the information, tutorials. You can look at the data from past assessments in many, many different ways, ranging from states and counties all the way down to very small watersheds. So this is a pretty widely used website to look at climate information, and there's a ton of it on there. Next slide. So a couple things here. So we're going to be looking at a few of these types of plots here that I'm showing on the left. And so the bottom of the bottom axis on this plot is time, so running from 1950 to 2100. The vertical axis is some fields. So in this example, it's mean annual temperature. The black lines are, this has all been modeled by the global climate models and downscaled. The black line is the historical record. The envelope, and with the envelope, the gray envelope showing the range of model, the 80% of the models are within that range. The red line is the upper scenario, the SSP 585 in red. So that's the mean or average of all the models. And the blue line is SSP 245, which is the mitigation scenario that we're considering. So what you can see from this is, compared to the 1981 through 2010 average, at the end of the century, the SSP 245 will warm about 5 degrees warmer than present, whereas the SSP 585 will be 11 degrees warmer. So I'm using these interchangeably. The upper one is for the previous assessment called RCP 8.5, and the lower one is for the newest assessment, SSP 585, but the scenarios are very similar. So the interesting thing about this, and I think pretty important thing, is these two different assessments, 7 years apart, pretty much come up with the same trajectory for warming and the same absolute amount of warming that's projected in the future. And this is with different climate models, slightly different scenarios, and different downscaling. So these climate projections have been consistent since the 1970s. In fact, we've known the effect of CO2 on the atmosphere since the 1800s. It's a pretty simple experiment to do in a test tube. So anyway, these assessments have been consistent for a long, long time, which gives us a lot of confidence that at least in terms of the forcing from greenhouse gas emissions, the models are getting it consistent. The other thing to notice here is that there's a trend. So these temperatures are trending up, which thinking back on Kathy's 800,000 year record, when CO2 is going up, temperature's going up. When CO2 is going down, temperature's going down. But also there's variability. And so the Gallatin County example is a good example that while there's a trend, year to year, decade to decade, there's going to be variability, such as, and so the cold spell that you just experienced a few weeks ago, et cetera. So we're increasing, but there's still going to be variability throughout the record. Next slide, please.
Steve, you might mention that the trends are pretty similar through the middle of the century, regardless of what scenario we're on.
Oh yeah, that's true. Yeah, through the middle. Well, and that's because the greenhouse gas emissions start to, the mitigation starts to really kick in around 2040. So yeah, they start out the same. Next slide, please. So this is what snow looks like from our climate or GYA assessment. This is GYA wide. This is from the AR5. So the upper row is our maps of the GYA, and areas that are snow dominant are shown in blue. Areas that are mixed rain and snow are shown in the red colors, and all rain is shown in green. So the first period is 1986 to 2005. And as we go from left to right through the century, you can see that at the higher elevations and the mid elevations start to lose snow dominance pretty early on. And that's replaced by rain and snow mix and increasing areas of precipitate or rain only. So when we look at the end of the century on the far right, there's really not a lot of totally snow dominant area left in the GYA. A lot of it's changed to rain snow mix and increasing amounts of rain dominant. The lower plot runs from 1950 through 21,000. And it shows just an elevation profile of how this is changing. So we start out with a lot of area in 1950 that's snow dominant, and by the end of the century, you can see that's really decreased quite a bit and been replaced a lot by rain and snow mix. And this line about 8,000 feet, as Kathy pointed out. We're seeing loss of snowfall there. That's pretty much the center of the things in the future in terms of how the distribution of rain and snow is going to change, could possibly change. Next slide. So we're going to look at the rest of this. We're going to look at an area around Bridger Bowl. Basically, the big belts. I clipped this out of our data sets. We need to look at an area rather than a point. The models are not really designed to be able to look at a point. So what I've done is clipped out this area that's shown on this map and done all the averaging of what I'm going to show you over this area. So it includes also, obviously, the high elevations, the mid elevations, and some lower elevations. But we need to do it this way because we really cannot focus on one single point, given the limitations of the models. Next slide. So this is what the area, including the ski areas, this is the projected mean annual temperature through 2100. So this is the annual temperature. By the end of the century, depending on which scenario we end up following with greenhouse gases, we could warm anywhere from 7 degrees to 12 degrees on an annual basis. So basically from 38 to 45 or 38 to 50 degrees at the rate, and the rates are shown below. So with the SSP 2.45, the rates, as Kathy was talking about, rates have changed 0.61 degrees per decade versus a really large 1.27 degrees per decade in the SSP 585. Next slide. So to divide this up, so we can look at how this affects winter temperatures. This is the change in winter maximum temperatures through the century, and you can see that by the end of the century, there's about a 9-degree warming for the warm scenario and a 5-degree warming for the cooler scenario during December through February. Next slide. Minimum temperatures, though, this is pretty much the case everywhere. Minimum temperatures will warm to a greater extent. So the temperature would be up to 13 degrees warmer by the end of the century with the warm scenario, and 8 degrees warmer with the cold scenario. So substantial warming of winter temperatures for sure. Next slide. In terms of precipitation, the lines show that by the end of the century, there is probably going to be a slight increase in winter precipitation. So it's not really getting drier, it's actually getting slightly wetter. But the form of that precipitation is going to change, or at least be modified somewhat from what it is now. Next slide. So this is how it affects snow. This is the snow water equivalent average over the entire big belts. So it's somewhere around 8 inches through 2020, and then starts to drop off in from 2020 out to 2100. On the right, I have the loss relative to 1981, 2010 for the period, the 10 years from 2025 to 2034. And you can see just in that period, there's either a 4 or 6% loss, depending on scenario. By 2035 to 2044, there's a greater loss of 13 to 22%. And by the end of the century, there's a 25% or 30% loss in March snow water equivalent. So pretty much the peak of the year potentially could go down by that much. So these are pretty substantial potential changes. It's not a forecast of what it might be like in a certain year, but what it is a projection of a possibility or probable outcome based on the greenhouse gas emissions that are in the projections. So next slide. So with that, what does climate change mean for all of us? Next slide. In terms of your area, probably a shorter season. The snow will come later and probably melt sooner. So a shorter snow season overall. Next slide. Uncertainty, there's lots of uncertainty. There's uncertainty in the model projections. There's uncertainty in how the future may unfold, with the idea that there's variability. There's existing variability, and that variability may change in the future. Next slide.
I think we also should add that there's uncertainty in the occurrence of climate-driven weather events.
Yeah.
So
yeah, the variability, yes, because we don't know a lot about the extremes could change, and so could change. There are a lot of things that could change. Absolutely. Next slide.
Extreme storms, rapid snow melt, yeah, floods, that kind of thing.
Obviously, more wildfire, and we're seeing that now, and that's going to definitely increase in the future. Next slide. And more people. This is actually Minneapolis skyline overlaid on Bozeman. I doubt it will ever look like that, but more like what we're seeing here in the foreground, more of that. But yeah, living with more people. So the whole ecosystem is experiencing change and will continue to experience change, definitely at different rates through the future. Next slide.
Yeah, Mountain Journal projected that by 2065, given the population growth that we're seeing now in Bozeman, we would have the population of Minneapolis proper. So they produced this slide just to horrify us.
Next slide. So thanks for inviting us in, and I hope we've given you some information that you can think about and maybe somehow use. Thanks.